Well, obviously, first things first, thanks to the organizers for getting us back in person to Beyond IID. For me, it's the first time in many years. I don't know about the rest of you. So I'm still totally thrilled to see so many of you so close up. I'm very sad that my co-author of this work, Andy, couldn't come. So he did this work. He was in IIT Kharagpur. Now he's doing work in Tata Institute in Mumbai. It was very convenient for him. I'm sure he would love to come. So I have to stick with this talk. So the reference is down here. The paper is already a little bit old. We only snuck it in here because we didn't present it in previous Beyond IID. And well, I mean, I'm just going into the description of the problem and as fast as I can, and then we have the results. So we are looking at entanglement-assisted class and quantum hierarchical control. So this is like a triple trade-off coding problem, which is probably very familiar to people having looked at it in the channel setting. We are basically using this in a setting of error-corrected codes. It's very similar. The difference is that in error-corrected codes you have 0 error. So sorry for the fonts, and I had to convert this to PDF. I mean, it's now the letters missing. So we have 3 resources: classic communication, quantum communication, and shared entanglement. That's kind of given amounts initially. Then, of course, the channel, that's kind of the usual thing in channel theory, we want to communicate through a channel. So we're using all of this to transfer some information from Alice to Bob, which is partitioned. There's some classical part, there's some quantum part, so numbers of bits. We should imagine there's a C1, a C2, and a C1 and Q1 and the E1 here. And we prepare also entanglement. So any of the resources that we want to produce, and ideally, of course, you think of it in terms of, well, it's a quantum channel, it can produce entanglement, it can communicate classically, it can communicate quantumly. So that's kind of the desire here, but we also allow some amount of it before. So the way this is used, it looks like this. I'm going to draw also the communication diagram. We have the communication here. That's Alice's message. Then we have the qubits. Well, we do this by having a maximum entangled state between Alice and the reference system. Then there is the entanglement, where this is between Alice and Bob. So this is kind of some general state. Yeah, it's good that you can't see this because maybe you would have checked on it. So let's see what you say. So obviously, we're doing channel theory style or coding theory style. So when I say number of qubits, number of classical bits, that's a sort of a combinatorial. So this is the dimension of the Hilbert space, so it's the length of the string. The entanglement, we chose for the purpose of this work to measure by the entropy of entanglement. So this the entanglement is just an arbitrary pure state. And it's a reduced state entropy. So if it's a maximally entangled state, then it's the number of qubits that are entangled. The reason why we do this is just because the analysis proceeds entirely in terms of phenomenon entropy. So it's more, it's just, you don't lose anything by doing this. Yeah? And so yeah, the entanglement is shared. These registers are here. Alice has to do some encoding, well, with the stuff that's available to her, obviously, her quantum message, her classical message, her shared entanglement. Okay, let's put this here. So this is the classical message, this is the quantum message, it goes and we use the noisy channel. And then Bob's decoder comes here, that again uses everything that is available at the time, including the channel output. And so Alice keeps only this here. This is what this will be. This will be the entanglement shared at the end with Bob. And then what Bob wants to receive the quantum message, so he should recover the maximum entangled state of reference, and you should get the message and faithfully. So that's kind of that's sort of Shannon theoretical standard. And yeah.
What is W?
Oh, sorry?
The W.
Oh, W is a quantum register and V is like a classical register. So these blue lines, these blue thick lines, they are sort of decohered registers. Everything else is in a big pure state. Sorry. Yeah, obviously I'm not going to write the definition of the code, so the diagram should suffice. Otherwise, I have to look at the paper. And yeah, we're looking in the zero error regime where this has to come, like this state has to be some state perfectly pure. This maximum entangled state has to come out exactly the same as it was here, and the message should be the same that comes out here. But of course, you can ask exactly the same question in the channel theoretical setting where all of those have error parameters. And then the channel might be, you know, some asymptotically large channel, maybe IID or not IID. And yeah, so how we account for the resources, or what is kind of our figure of merit, is the catalytic gain in resource. For example, the difference between the initially provided communication and the final communication. So this V has a certain bandwidth, that's C1, and we communicate a message of C2 bits, so the difference, that's kind of okay. And Q is similar. And for entanglement, for historical reasons, because we're the first one to look at this problem, we're not looking at the gain, we're looking at the loss. We're looking at how much is needed. I apologize for that, but okay, direct your wrath. It's actually Minshu is one of the people in the very first papers on this. It's like entanglement-assisted capacity. We do the same thing then. We look at how much entanglement is consumed to produce something. Just sometimes there's a sign problem in the mind. Okay, the capacity region, that's a sort of a notion from channel theory. We want to look at all the triples that are possible for a given channel. Yeah. So the real numbers, these are real numbers potentially. And so to explain one part of the one term in the title, Singleton bound. So this is a notion from classical error correcting codes, a particular combinatorial bound on the size of a minimum distance D code. So the way you should think about this, the way I think it's kind of it becomes, you can use Singleton bound sort of in almost all channel theoretical settings. That's the bound on your code that you get when the channel is in the erasure channel. Yeah, why is that? Because the minimum distance D code, that is precisely a code that can correct all errors of an erasure channel that erases up to D-1 symbols. That's an equivalent description. And so channel theoretical, of course, depends always on the channel. So we're looking at this particular channel. So we're saying, okay, what kind of bound do we obtain on our code? If you just look at this through our channel theoretical with an erasure channel. So I should straight away go kind of to an important distinction. So in general, in this talk, I will consider two different types of erasure channel. There's of course a very important case of the IID erasure channel with with input and output dimension Q and erasure probability delta. So that's the probability that the input is erased and replaced by a sign that the state is lost. And for the coding theory, you're looking at a block erasure channel. So you have n input systems, each of cardinality Q, so a Q-ary coding. And the channel randomly selects D-1 of them and erases them and transmits the others. And it tells the receiver which of them were erased. Yeah, so that's the erasure. And so I repeat, all these definitions of quantum error correcting codes, that whenever they talk about minimum distance, it means this code is able to decode the message from the output of this erasure channel. That's just, I mean, this is not a definition, this is a lemma. It's an equivalent description of when you look at the coding theory literature, they talk about correctable errors and syndromes and so on. It's for our channel theories, that's what it is. I mean, it's one of many equivalent descriptions. And yeah, so this is the one that I want. So when we talk about a hybrid entanglement-assisted error correcting code, hybrid means that there's quantum and classical transmission. With minimum distance D, it means that it does the job in this diagram, this communication diagram, the zero error, and for this particular channel. So where n is the number of blocks, Q is the size of the alphabet, so the dimension of the global interface, and D is the minimum distance. So those are parameters that in error correcting codes you always have to kind of, they are fundamental. So the Q is oftentimes just implicit, sometimes two, we get general here. Because the Singleton bound is kind of agnostic to it. And then exactly, when you have the number of qubits you can encode and successfully decode, the number of, well, in our case, it's much more complicated. There's also classical and there's the entanglement, which is why, I mean, I personally prefer to look at these communication diagrams than to write the abstract decodability conditions. And so, yeah, this setup and the results I'm going to present, it includes special cases things that were known before. So obviously you have to start with the classical singleton bound from quite a few years ago. So the channel would be basically a classical erasure channel, of course, here. And then the number of bits you can send is bound by n minus n plus 1 times the log of the alphabet size. So, and Singleton obtained this basically just by counting. It's a combinatorial argument, but you could also think of it as an information bound. That's the capacity of the erasure channel. And so clearly you can't do anything about it. Then there's the quantum singleton bound. So we have a quantum erasure channel, the one I showed in the picture. That it takes qubits or qubits, whatever it's called. So if this is this block erasure channel, the number of qubits you can send, ignoring all the other parameters, is this here. It's n minus 2d plus 2. So this kind of loss you have, this subtraction of d minus 1, it's doubled here, log q. So this can be negative when d becomes larger than n over 2. Then you don't have any capacity. That's why I have this stupid maximum. Either it's this one, and if this part becomes negative. And well, in previous work with Markus Strassel and Felix Huber, we looked at a sort of a simplified version of this when C is 0. So we have only Q and E, only quantum transmission and quantum entanglement. And okay, we get a two-dimensional region. We get a polygon described by linear inequalities, which I'm not going to reproduce because the others, they are barely more complicated ones I'm going to write for the channels. And okay, so to come back to the history a bit of the problem, Minshu here together with Mark Wilde, and then in much more detail Mark in his famous book, have considered this in the channel theory setting when this here is actually n copies of some noisy channel. So n tensor power n. And there's sort of a channel theoretical, not single letter characterization of the capacity region. Okay, so I'm just going to walk you through the main results and discuss them a little bit because after all, these talks we don't have so much time. So this is basically recalling what we get. And basically all we do is we simply we use the same analysis of Minshu and Mark for this one-shot channel, because obviously we don't want to be stuck with a tensor product channels. We want to apply to this block erasure channel in particular. So we first go through this, and it all works out. I mean, it's basically because you have to have a regularized converse anyway. So all these upper bounds, they are information converses, which information between the A and B are the inputs and the output of the channel. U is some auxiliary variable that you need to describe to analyze the code, and you get here a quantum information, you get coherent information of various types. And you of course have your resources. So you have this is for example E2, the log of the, well, kind of. Yes, this should be. Oh no, there's the epsilon. Sorry. Why is there not? Oh no, because no, sorry, apologies. These epsilons here, this is just because I'm just reproducing the result of them with error. So when epsilon is 0 from the collision, they said these are not here. And so then you have to specialize it to the erasure channel. And it turns out this is very easy if you do it for n equal 1. You just look at the set of couples you can get if you take the union of all, say, sigma of this form, you get this here. So delta is the erasure probability, and t is some kind of free parameter which is bounded. Yeah. And so for n equal 1, it's almost an exercise. And basically you just have to realize for the erasure channel, because of the simple structure of the erasure channel, the entropies that appear here, they can all be written in terms of some very few basic and simple quantities, and then you're left to studying the relation between those. The problem is then the singularization. If you want to prove that when n is larger, you get exactly the same rates. I mean, this would be number of bits divided by n, to be honest. We put an n in front of here. So our proof actually, the older proof, it uses something like the gradability of the erasure channel for delta less than 1/2, and for delta larger than 1/2, well, it should be simpler because it's anti-degradable, but somehow the argument doesn't work anymore. So we fixed that here in this paper, but I'm not going to discuss it because it's a bit intricate. I mean, let it be said that what we do is we reduce it actually to the block erasure channel. You think that this should be easier, but it turns out no, this is much easier to analyze. And so this is the main result. This is the Singleton bound for these triple resource codes. Yeah, so if you have a code of block length n, doing distance d, local alphabet size q, and it transmits C classical bits, Q quantum bits, and net entanglement consumption E, then necessarily there exists a T such that this is true. That is the theorem. So, and yeah, I mean, like I said, you basically get this from massaging these expressions here for the case of the block erasure channel. So a lot of symmetry. So this maybe one of the reasons. Maybe I should throw this in right now, because surely some of you will be thinking, why the hell does he use phenomenology? It's a one-shot problem. You should be using our beautiful one-shot entities. You've worked on this, we've worked on this. There's probably an optimal characterization. The problem is, well, it's hard to evaluate it. And because of the symmetry, because there's so much symmetry, you get away with the phenomenon entropy. That's the main reason. It's like, you know, when you have a sufficiently symmetric state on many bodies, well, you have almost a coefficient property, and you don't need all this other entropy. So, so I'm gonna discuss now the result, because I think I have a couple of slides later on about ingredients of the proof. I will see how they're going to define, which yeah, sort of going. So I just want to show what this region looks like, because it's a region in 3 space. So there's this annoyance of these 3 parameters, but actually it turns out to understand the geometry is useful, because if you fix T, you get these kind of Simplicia cones. I mean, I'm not exactly sure if it's pointing in the right direction. It's open because there's no positivity requirement here. And so for each T, you get this Simplicia cone that's hanging from an apex. And just with T, it's just the apex changing. So you have this interval. This is very important. And so at the endpoints, we have, for example, this corresponds to C equal to this and Q equal to 0. It's a classical code for the erasure channel. We know the capacity is this one. And this is C equals 0. This is the entanglement-assisted capacity of the erasure channel, which is this one here. That's Q, 1 minus delta times alpha block alpha size. And this happens to be the optimal entanglement consumption you require to achieve that, which is a cute thing, actually. If you haven't seen it, I want to point this out. We tend to think of delta kind of small. Okay, then you get a large capacity, and you just need a bit more of entanglement. Think of delta large, delta close to 1. You almost get no capacity, but to get that, you need to spend a lot of entanglement. Almost like the whole, delta could be 1. I mean, if it's 1, then of course it was 0. If it's close to 1, you can still communicate, but the price is an enormous amount of entanglement compared to what you can communicate. We know that this is optimal. And so how do we get the Simplicia cones? Well, again, the first thing to focus is, well, what does it mean to move from the apex along one of those edges here? And so it turns out this corresponds to composing the code here with one of 3 elementary protocols to get another code. So it's a concatenation argument. You use teleportation that allows us to convert some amount of classical communication quantum entanglement into quantum communication. Right? So we can exchange at linear rates triples of contributions. So, but it's coding does something similar, only in the opposite direction. And then there's a stupid protocol. If you can communicate a quantum bit, you can also create entanglement. And so those are these 3 things. And the rest you can get just by time sharing. I mean, this is like an IID channel. So we can just use some scheme on a sublog, there's another scheme on another sublog. So if you can make this here, these 2 points, and all of these lines also over here, I can get the whole blue region, at least in the asymptotic region. So that's kind of the proof that this is the rate. And for the relation channel, of course, it's a bit different because all these numbers here, C, Q, E, they are log of integers. So it's ultimately it's a discrete thing, while the difference is lots of integers. So actually maybe it's almost continuous. And so we have a similar thing. We know here these codes, well, if you have a code of this type, it's a classical code, no quantum. Oops, with no quantum contribution. Such codes actually exist if the alphabet size is big enough. This is a topic in coding theory. If you have small alphabet size, then Singleton bound is not tight. But if it's large, then you can do it. And this is a similar thing. This is what is called a maximal entanglement quantum error correcting code with entanglement assistance, but no classic communication. And so this is the maximum rate you can get, and this is the corresponding necessary and sufficient amount of entanglement. And again, if the alphabet size Q is big enough, then such codes exist, but for smaller sizes, sometimes they don't. And that's why coding theory is a difficult and non-trivial topic. And so, yeah, we can move along these edges, at least in discrete steps, by using teleportation, installing, and Swiss conversion. And the big problem we have is time sharing. We don't know what's with this line here, because that be some kind of interpolation in a classical minimum maximum distance separable code and a quantum entanglement assisted code. And I haven't seen construction of such things. So this has been open since as well. And so let's see how I'm doing. I can have a little bit about the ideas that you have here. Well, like I said, we use the same von Neumann entropic converse for a general general single shot channel. And then we set epsilon equal to 0. So that's why we're not really bothered about those funnest terms. And then comes the thing. So because you have an erasure channel, so all of the quantities up here are, for example, well, this is a one-shot erasure channel. Sorry, single copy of erasure channel. You have two important quantities, basically, entropy of the output of the channel. Oh, no, sorry, this is even the entropy of the input of the code and the average entropy. So this U is some kind of condition. And you have, on the block, you have kind of a similar thing. And because of the symmetry of the channel, it gives you the idea you should symmetrize. And you should, I apologize if it's a bit small, but so it turns out for the erasure channel, you can express all of those information quantities that appear in Scheer and Wilder's converse in terms of these elementary quantities for L specific interesting block lengths. So L is the length of a block, so I is a subset of the N systems, and you're averaging over all the different blocks of size L of this N, of some reference state. And here you have the same thing conditioned on U, so which is like an average. And then you normalize with the block length. So all of these guys here, this S hat and S bar, they are between 0 and log Q, because they are sort of an average entropy per system. So they obey certain inequalities between them. For example, S bar is less than or equal to S hat because I have the only difference is the clear condition on U, so it's Strong's relativity. Another application of Strong's relativity gives you that SL hat and also SL bar is decreasing with L. So it's the largest, it's for small L, and it's the smallest for L equal to N. There's a little lemma that has a long bit of fun history. And so we need this only, for example, for L equal to D minus 1, or L equal to N, and N minus D plus 1, and numbers like this here. And you just play around with this, and you use, I promise, nothing but Strong's relativity, and you get this result. So another, so this is the part about the proof that I wanted to say. Another thing is you can eliminate the parameter. This is in convex geometry. It's called Fourier-Motzkin elimination. For one parameter, it's a simple thing. You get a bunch of more complicated inequalities, but now there is no parameter t, so you can see well this is a polytope, obviously. Unfortunately, you have to, because of the nature of the elimination, you have to distinguish between two cases if delta is less than 1/2 or larger than 1/2. And so that gives you two different shapes of the region. I mean, they look very similar, but you see in one case, because you have these two simplices here hanging from the apexes, right? In one case, well, in either case, one of the edges of the simplex ends up in the interior, but in one case, it's the edge hanging from t equals 0, and the other one is the edge hanging from t equals log Q. So yeah, well, anyway, so you actually only have 5 extreme arrays, not 6. And yeah, so maybe with that I will stop because then we have a bit of time for questions. So the the upper bound, what I wrote here, that's what you see here, we actually proved, like I said, we proved it first. We proved it first for the block erasure channel, so where there is an n always on the right hand side, because the x's are non-normalized numbers of bits, not rates. And then, so maybe the final thing, since I have a couple of minutes, the way we then get the statement that the same bound applies for the IID small erasure channel is the realization that the IID erasure channel is a complex combination of those block erasure channels, right? Because the IID erasure channel also has the same symmetry. There's just this Bernoulli variable for each of the n systems that decides erasure or not. So you can group the erasure events according to cardinality. D minus 1, how many systems are erased, but then which ones are erased is completely symmetric. So the IID erasure is just a mixture of block erasure channels. And so that means and each block erasure channel can be obtained from a smaller noise block erasure channel by erasing more. I mean, if you have an erasure channel that gives me that erases D minus 1, well, I can just erase another bit and just append a little bit more noise to erase D. And so from that it follows, well, I can actually simulate the IID erasure channel with the block erasure channel, and approximately I can also simulate the other way around. And so, yeah, that means I can at least approximately import the converse from one to the other. So we have the zero error converse and the epsilon converse for the block erasure channel, and that gives us the epsilon, the weak converse in the Shannon theoretical sense for the IID erasure channel, which I repeat was known, but only for small enough delta. For some weird technical reason, I'm still struggling to understand why we cannot make a direct proof, sort of ordinary single legislation for the block for the IID. And that's it. I think I should stop here. There are some references.
You have time for some questions? Just wondering, so essentially you also generalized the classical Singleton bound, because I guess the never considered catalytic.
Yes, yeah. I mean, but yeah, it's kind of triggered. Yes, yeah. I mean, okay, coming to that, of course, there you can ask a more refined question, because of course, I mean, when you say, how can we attain those bounds? Maybe you can attain some triple C, Q, and E, and let's say C and Q are positive, and E is also, I mean, you actually achieve communication with some entanglement consumption. Can you actually do it without catalysis? I mean, that's a very important question. I mean, it's a non-trivial question. Even though it's C and Q are positive, it doesn't mean that you can achieve it with as a C1 minus 0. That's not even some kind of approximation. There are hard constraints. Even if C is the log of an integer, we can't necessarily do it. But it's like there are coding theoretical reasons and rigidity of codes. So in the paper with Markus Grassl and Felix Huber, we cite an example of such a thing, of a catalytic code that to generate entanglement, but you cannot do it without having a little bit of entanglement to start.
Yeah, no, I'm just wondering whether classically maybe also some things.
Yeah, I think for if you only look at the classical thing, it's a purely combinatorial effect. So I don't think it will happen. But I'm not. I'm not sure.
There might be more optical codes.
Yeah, fair enough. Yeah, okay, that might be an interesting case study. So anyways, there's clearly a more refined study to do that you actually study 6 parameters. So for each achievable C, you want to know what are the pairs C1 minus A2 that are actually realized. So we haven't gone there, obviously, it's too much. Yeah, that's good.
So it's just a correction, not a comment. So the third paper is actually from 2010.
Oh yeah, sure. Yeah,
2001.
Yeah.
It looks really old.
Oh yeah. Yeah, Winter did this when he was in high school. You know? Yeah, I mean, it's better you look at the paper because they're the reference on I believe. Okay. Thank you very much.
Let's thank Andreas again.